In October 2019, inside a cold storage room at Google's campus in Santa Barbara, California, a machine completed a calculation. That sentence sounds ordinary. Machines complete calculations all the time. Your phone is completing billions of them right now just to display this video. But this particular calculation was not ordinary. It was not ordinary in a way that the engineers who built the machine could describe in precise technical language, using the correct equations, citing the correct literature, and still somehow fail to communicate the thing that should have stopped the world. The machine was called Sycamore. It was a quantum computer, a device whose components are not transistors made of silicon but superconducting circuits cooled to temperatures colder than outer space, operating on principles so counterintuitive that Richard Feynman, one of the greatest physicists of the 20th century, once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. Sycamore performed its calculation in 200 seconds. 200 seconds, 3 minutes and 20 seconds. Google's engineers calculated that the same computation, performed on Summit, at the time the most powerful classical supercomputer in the world, would have taken approximately 10,000 years. 10,000 years. The agricultural revolution happened roughly 10,000 years ago. Writing was invented about 5,000 years ago. The entirety of recorded human history fits inside the time it would have taken the best conventional computer on Earth to complete what Sycamore did in the time it takes to soft-boil an egg. The announcement made international headlines. Satya Nadella of Microsoft tweeted about it. The Financial Times ran a front-page story. Politicians spoke about it in terms of technological supremacy. Researchers in cryptography began urgent discussions about whether encryption systems protecting global banking and communications needed to be redesigned. And none of that, not the financial discussions, not the cryptography panic, not the geopolitical maneuvering about who would win the quantum race, none of it touched the question that should have been the first question. The question that every journalist should have asked in every press conference. The question that, if you sit with it long enough, does not lead to a conversation about better computers or faster drug discovery or more powerful artificial intelligence. It leads somewhere else entirely. The question is this: where did that calculation take place? Not in the sense of which building, which room, which country. In the sense of where, physically, in the universe, did the computational work happen? Because Sycamore is a chip with 53 qubits, 53 quantum bits. Each one is a tiny superconducting loop, a microscopic physical object sitting in a refrigeration system in California. That is a specific, finite, bounded physical system, and the computation it performed, a computation that would have required 10,000 years on the world's best classical computer, used far more computational resources than that physical system by any classical accounting appears to contain. The computation happened somewhere. Somewhere, something performed the work. But if you follow the physics carefully, if you trace the mathematics of what quantum computers actually do and how they actually do it, you arrive at a conclusion that a growing number of physicists believe is not a metaphor, not a figure of speech, not a philosophical flourish, but a literal description of physical reality. The calculation happened in other universes. I know how that sounds. I know what it sounds like when that sentence appears in a YouTube video about quantum computers. It sounds like the setup for a pseudoscience rabbit hole, for a monetized conspiracy, for the kind of confident overclaiming that has given popular physics coverage a reputation for unreliability. So let me be completely clear about something before we go one step further. What I just said is not fringe. It is not pseudoscience. It is not the speculation of outsiders peering through the fence at real physics and getting it wrong. It is the considered position of some of the most accomplished theoretical physicists alive, including David Deutsch at Oxford, the man who invented the theoretical framework for quantum computation itself, who has said, explicitly and on the record, that the only honest interpretation of what quantum computers do is that they perform computations across a vast number of parallel universes simultaneously, and that the power of quantum computing is, literally, the computational resources of those universes being harnessed. Hugh Everett, who first formalized the many worlds interpretation of quantum mechanics in 1957, Max Tegmark at MIT, Sean Carroll at Johns Hopkins, a list that is not a list of cranks but a list of physicists whose papers appear in Physical Review Letters and Nature, and who hold endowed chairs at the world's leading universities. and against them, an equally serious, equally credentialed group of physicists who say the calculation happened right here, in this universe, and that the appearance of something more is an artifact of how we describe the mathematics, not a description of physical reality. That the wave function is a calculational tool, not an ontological fact. That there is no sense in which Sycamore reached into parallel universes. Both groups cannot be right. And the question of which group is right is not merely a philosophical curiosity about the foundations of physics. It is a question about the structure of reality, about whether the universe we can see and touch and measure is the full extent of what exists, or whether it is an unimaginably small sliver of something vastly, incomprehensibly larger. It is a question about whether the laws of physics, followed honestly and without flinching, require us to accept a picture of reality so different from our intuitions that most people have never been given the tools to even confront it clearly. This video is about that question, not the comfortable version of it, not the version that reassures you at the end that everything is fine and science is making progress and the world is comprehensible, the version that the physicists actually have, the one that keeps some of them awake, the one that makes others reach for comfortable conventional interpretations not because the evidence supports those interpretations, but because the alternative is a description of reality so vast and so strange that it rewrites every assumption you have ever made about where you are and what you are, and whether the choices you make have consequences only here. Let's go. Chapter 1. What a qubit actually does, and why it's already impossible. Before we can talk about where the calculation happened, we need to understand what the calculation was doing, and to understand that, we need to understand what a qubit is, not the sanitized pop science version, but the real version, the one that already contains the problem in its most basic form. A classical computer bit has two possible states, 0 or 1. At any given moment, a bit in your computer is either a 0 or a 1. It is a physical object, a transistor, a capacitor, a magnetic domain, that is in one of two possible physical configurations. That's it. That's the whole story of a classical bit. Binary, definite, either or. A qubit is different. A qubit is a quantum mechanical two-state system, a physical object that can exist in a superposition of its two basis states. In the case of Sycamore's qubits, the physical object is a superconducting circuit called a transmon qubit, and the two basis states correspond to two different energy configurations of the circuit. When we say the qubit is in a superposition, we mean something specific and mathematical. The qubit state is described by a wave function that is a linear combination of the two basis states, with complex valued coefficients whose squares give the probability of finding the qubit in each state when measured. So far, this sounds like probability. Like the qubit is just uncertain. Like it's in one state or the other, we just don't know which. Like a coin in the air that we haven't looked at yet that is definitely either heads or tails, just unknowable until it lands. This is the interpretation that most popular science books reach for because it's comfortable and familiar. It is also, experimentally, demonstrably wrong. Here's how we know it's wrong. If a qubit in superposition were simply a coin in the air, definitely in one state or the other, just unknown, then its superposition would behave like classical probability. Two such qubits in superposition would produce correlations that fit within specific mathematical bounds derived from classical probability theory. These bounds are called Bell inequalities, derived in 1964 by physicist John Bell, and they specify the maximum correlations that can exist between two systems if those systems are merely uncertain about their states rather than genuinely in superposition. In 1982, experiments by Alain Specht and his collaborators showed definitively that quantum systems violate Bell inequalities. Their results were confirmed and refined dozens of times over the following 4 decades, culminating in the 2022 Nobel Prize in Physics, awarded to Aspect, John Clauser, and Anton Zeilinger specifically for experimental work establishing beyond any reasonable doubt that quantum superposition is not ignorance about a definite underlying state. It is something else. Something for which we don't have a good word in ordinary language because ordinary language was built to describe the classical world we experience, not the quantum world that underlies it. The Bell inequality experiments did something specific and important beyond confirming that quantum mechanics is correct. They ruled out an entire class of alternative theories, local hidden variable theories, that would have allowed us to say, the qubit is really in a definite state, we just don't have access to the information that specifies which state. You might have imagined that quantum mechanics is like not knowing which card was dealt to you from the deck. The card has a definite identity, you just haven't looked yet. Bell's theorem, and the experiments confirming it, ruled this out. The qubit is not like an unlooked-at card. There is no hidden card with a definite identity. The indefiniteness is not a limitation of our knowledge. It is a feature of the system itself. This is harder to accept than it sounds. The human brain evolved to navigate a macroscopic world where objects have definite positions, definite velocities, definite properties. The idea that a physical object has no definite value for a physical property until the property is measured, that the measurement doesn't reveal a pre-existing fact but instantiates a new one, cuts against every intuition built up by millions of years of evolution and decades of personal experience. But the experiments leave no room. The universe, at its most fundamental level, does not work the way our intuitions tell us it should. Objects can fail to have definite properties. That is the world we live in, and the quantum computer sitting in California was built to exploit exactly that fact. What is a qubit in superposition? Precisely. A qubit in superposition is a physical object that has no definite value. Not unknown, not uncertain, but genuinely physically ontologically indeterminate until the moment it is measured. The act of measurement does not reveal a pre-existing value. It creates a value, instantiating one possibility out of a range of possibilities that were genuinely all real until that moment. This is not a philosophical interpretation of the math. This is what the experimental record, after 40 years of increasingly precise tests, forces us to accept. Now, scale this up to 53 qubits. 53 qubits, each in a superposition of two states, collectively form a quantum system that exists in a superposition of 2 to the power of 53 states simultaneously. 2 to the power of 53 is approximately 9 times 10 to the power of 15. 9 quadrillion states. A classical computer representing the full quantum state of 53 qubits would need to store and manipulate 9 quadrillion complex numbers. This is why simulating a quantum computer on a classical computer becomes exponentially harder as the number of qubits increases. Not linearly harder, not polynomially harder, but exponentially harder. Each additional qubit doubles the size of the state space. At 53 qubits, the classical simulation has already become impractical. At 300 qubits, the state space contains more dimensions than there are atoms in the observable universe. Think about what exponential growth means here in concrete terms. Going from 1 qubit to 2 doubles the state space, from 2 states to 4. Going from 10 qubits to 11 doubles it from 1024 states to 2048. Going from 52 qubits to 53 doubles it from 4.5 quadrillion states to 9 quadrillion. Each individual qubit you add to the system doubles the entire computational resource. This is why quantum computers are so qualitatively different from classical ones, not just faster in some incremental sense, but exponentially more powerful in a way that compounds with every additional qubit. And that exponential growth in computational resource is occurring in a physical system whose size grows only linearly. Each additional qubit adds one small superconducting loop to the chip. The physical system grows by one component. The superposition space doubles. At some point, the superposition space is larger than the entire classical world, and then it keeps doubling, and doubling, and doubling. This is the computational resource that Sycamore accessed. Not 9 quadrillion transistors, not 9 quadrillion separate processors. 53 physical objects, cooled to 15 millikelvin, colder than the temperature of deep space, manipulated by precisely timed microwave pulses, performing operations on a superposition that exists across 9 quadrillion states simultaneously. And this is where the question becomes unavoidable. Where does that superposition live? When Sycamore's 53 qubits are in a superposition of 9 quadrillion states, each of those states is doing computational work. The quantum algorithm, the sequence of quantum gate operations applied to the qubits, is processing all 9 quadrillion states in parallel. This is the fundamental mechanism of quantum speedup. It is not magic. It is not a trick. It is the exploitation of superposition to perform parallel computation across an exponentially large state space. The The parallel computation is real. The work is real. The results, when the qubits are finally measured, encode information derived from computations performed across all 9 quadrillion states. The question of where that computation happened is a question about physical ontology. It is the question that the interpretation of quantum mechanics is, at its heart, trying to answer. And the different interpretations give wildly different answers. In the Copenhagen interpretation, the one most taught in introductory physics courses, the one that Niels Bohr and Werner Heisenberg developed in the 1920s, the question, where does the superposition live, doesn't have an answer because the question is considered meaningless. The Copenhagen interpretation holds that quantum mechanics is a tool for predicting the outcomes of measurements, and that asking about the physical reality of the quantum state between measurements is asking the wrong kind of question. The wave function is a calculational device, not a physical object. There is no fact of the matter about where the computation happened, because asking about physical facts outside of measurement outcomes is outside the scope of physics. This answer has the virtue of pragmatic clarity. It avoids the uncomfortable implications of taking the wave function seriously as a description of reality. But it has a cost. It makes physics fundamentally incomplete. It says there is a domain of questions. Questions about what is physically happening between measurements that physics either cannot or should not answer. For many physicists, this is intellectually unsatisfying to the point of being unacceptable. In the many worlds interpretation, developed by Hugh Everett in his 1957 Princeton PhD thesis, and subsequently developed by Bryce DeWitt, David Deutsch, David Wallace, and others, the wave function is a real physical object, and the computation happens everywhere the wave function says it happens. When Sycamore's 53 qubits are in a superposition of 9 quadrillion states, all 9 quadrillion states are real, physical, equally existing branches of reality. The computation happens across all of them simultaneously, in parallel realities that are each as real as the one you're experiencing right now. The power of quantum computation, in this interpretation, is the power of recruiting computation across a vast multitude of parallel realities. In the pilot wave interpretation, developed by Louis de Broglie and David Bohm, the computation happens in this universe, guided by a non-local pilot wave that carries information about the quantum state. The pilot wave is real, the particle is real, and the apparent parallelism of quantum computation is a consequence of the pilot wave's non-local structure. It somehow encodes and processes information about the full quantum state, even though there is only one physical system. This interpretation preserves the single universe, but requires the pilot wave to be a real, non-local, instantaneous influence on the particles it guides. An interpretation that creates its own profound puzzles about the structure of space-time and causality. In other interpretations, cubism, relational quantum mechanics, consistent histories, the answers vary further, each trading one set of conceptual difficulties for another. What all of these interpretations agree on is the mathematics. The equations are unambiguous, the experimental predictions are identical. The disagreement is entirely about what the mathematics means, about the ontological status of the wave function, about what is real. And this is the specific point where quantum computers, in October 2019, stopped being simply an engineering milestone and became a philosophical crisis. Because Sycamore didn't just demonstrate that quantum computers can solve specific problems faster than classical ones. It demonstrated, concretely and measurably, that the computational resources available to a quantum system are exponentially larger than the resources available to any classical system of the same physical size. It made the question of where those resources come from not a theoretical puzzle, but a practical engineering reality. Where did the computation happen? The engineers needed to know, the physicists needed to decide, and the answer they give will determine not just how we understand quantum computers, but how we understand everything. Chapter 2: The experiment that changed physics forever, and the question. Nobody asked. Let's go back to October 23, 2019, the day the Google AI quantum team published their results in Nature. The paper's title was clinical, precise, and completely failed to communicate its significance to anyone without a physics background. Quantum supremacy using a programmable superconducting processor. Supremacy, a word that would later be replaced by the more politically neutral quantum advantage, but which at the time was the standard technical term for the milestone being described. the point at which a quantum computer performs a computation that is, for all practical purposes, impossible on any classical computer. The task Sycamore performed is called random circuit sampling. It is, frankly, not a task with obvious practical applications. Sycamore was not asked to factor a large number, which would break RSA encryption. It was not asked to simulate a drug molecule, which would revolutionize pharmaceutical development. It was asked to sample from a specific probability distribution over bit strings, to essentially roll a very complicated quantum die and report what came up, in a way that statistically matched the predictions of quantum mechanics. The choice of random circuit sampling was deliberate and smart. It is the easiest task to benchmark against classical computers. The classical simulation of random quantum circuits is known to scale exponentially in the number of qubits, and the difficulty of classically verifying the results is manageable for the specific circuit depths chosen. It was designed precisely to demonstrate the quantum advantage clearly, not to do anything useful with it. IBM, whose own quantum computing program is one of the most advanced in the world, pushed back on Google's claim almost immediately. They published a blog post arguing that their own classical supercomputer summit could simulate the Sycamore computation in approximately 2.5 days, not 10,000 years, by using a more memory-intensive classical algorithm. Google's team responded that IBM's estimate required 33 petabytes of memory, more than the entire digital data storage capacity of the United States government, which would make it impractical on any currently existing hardware. Both sides were being precise and honest. The argument was about which parameters to use to assess the difficulty of classical simulation, and both answers were technically defensible. The back and forth between Google and IBM was covered in the tech press and quickly forgotten. What nobody in the tech press, and remarkably few in the mainstream physics press, commented on was the underlying physics. Let's think about what random circuit sampling actually is, at a physical level. Sycamore's 53 qubits begin in a simple, known initial state. Then a sequence of quantum gates, mathematical operations on the qubits, is applied. Each gate transforms the quantum state of the qubits according to the laws of quantum mechanics. The gates are chosen essentially randomly. They are a pseudo-random circuit, a specific sequence generated, by a controlled random process. After the circuit is applied, the qubits are measured, and the measurement results are recorded as a bit string. This is done repeatedly, thousands of times, and the distribution of bit strings is collected. The claim of quantum supremacy rests on the fact that this distribution is extremely hard to compute classically, because computing it requires simulating the quantum evolution of all 9 quadrillion states simultaneously, which means that to produce the correct distribution, the quantum computer is, in some physical sense, actually exploring all 9 quadrillion states. It is not merely producing random outputs, it is producing outputs that encode the statistical structure of an exponentially large quantum computation. Where does that exploration happen? This is the question. And the fact that it was not loudly and publicly asked in October 2019 is, I think, one of the most significant silences in recent scientific history. Not because the physicists didn't know the question, they knew it intimately, had been arguing about it for decades, had written thousands of papers about it, but because the journalists who covered the announcement and the public who read those articles were given a narrative about a technology race and a cryptography threat and a geopolitical contest, and were never shown the thing that sits beneath all of that, the thing that makes the technological implications almost beside the point. David Deutsch, in a 2001 lecture at the Santa Fe Institute titled The Fabric of Reality, put it this way: if a quantum computer with 300 qubits were to perform a calculation, it would have to be working on more numbers simultaneously than there are atoms in the observable universe. Where are all these intermediate results being worked out? He answered his own question without hesitation. They are being worked out in other universes. Deutsch is not a casual observer of this question. He is the person who in 1985 wrote the theoretical paper that established the concept of a quantum Turing machine, the foundational document of quantum computing theory. He has thought about this question more carefully and for longer than almost anyone alive, and his answer, other universes, is not a metaphor. He means it literally. He believes it as firmly as he believes in the existence of the chair he sits on. The question is whether he is right. Let's look at the structure of what quantum computation does at the level where the interpretation question becomes inescapable. Quantum algorithms work by preparing a quantum system in a superposition of many states, performing operations that create interference between those states. Constructive interference where the correct answer is encoded, destructive interference where incorrect answers are encoded, and then measuring the system to obtain the correct answer with high probability. The interference is the key. It is the mechanism by which quantum computers are able to do something more than just sampling from a probability distribution. Without interference, a quantum computer in superposition would just be a probabilistic classical computer, one that randomly explores possibilities but not systematically amplifies the right ones. With interference, it becomes a device that exploits the wave-like nature of quantum states to cancel out wrong answers and reinforce right ones. Interference is a wave phenomenon. Waves interfere when they overlap and add together, with crests reinforcing crests and crests cancelling troughs. For quantum mechanical interference to work, for the wave function of a 53-qubit system to produce interference between its 9 quadrillion components, those 9 quadrillion components must be in some sense real and present, because only real present waves can interfere with each other. You cannot have interference between something and nothing. You cannot have a wave that interferes with an absent wave. This is the core of Deutsch's argument, and it is in its basic structure compelling. The interference that makes quantum computing powerful is physical interference. It requires the components of the superposition to be physically real in some sense that allows them to interact. If only one component of the superposition is real, if the others are just probability labels, then there is nothing for it to interfere with, and the interference effects that give quantum computers their power should not occur. The response from Copenhagen-flavoured physicists is that the wave function is a mathematical object, not a physical one, and that mathematical objects can interfere with each other without any corresponding physical entities. The wave function evolves unitarily. The interference is correctly described by the mathematics, and the measurement outcomes are predicted accurately. Nothing in this picture requires us to posit the reality of the other branches. They are calculational artifacts. Deutsch's counter-argument is that this explanation, the wave function is just a mathematical tool, has never been cashed out in a physically coherent way. If the wave function is only a calculational tool, what is the tool calculating? What is the physical process that it describes? The tool gives the right answers is not an explanation of what is physically happening. It is a description of the tool's utility. And if the tool's description of a physical process involves quantities that we are not allowed to take seriously as physically real, then the theory is, in some important sense, incomplete. He is right about the incompleteness. The Copenhagen interpretation, taken seriously, implies that there are questions about the physical world, questions about what is happening to quantum systems between measurements, that physics either cannot or should not answer. Most physicists who work day to day with quantum mechanics simply don't think about this. They use the formalism, they get the right answers, they don't ask the uncomfortable question. This is sometimes called shut up and calculate, and it is a perfectly serviceable methodology for doing physics without going mad, but it is not an answer. Chapter 3. The Many Worlds. What Everett actually said, and why it's terrifying. Let's talk about the many worlds interpretation properly, not the comic book version, not the science fiction version where parallel universes are places you can visit, where a version of you made different choices and lives a different life in a way that is basically just a narrative device. The real version, the one Hugh Everett actually proposed that David Deutsch actually defends, that a substantial fraction of working physicists actually believe. The real version is stranger than the fictional one, and it has a specific implication for what quantum computers are doing that most popular presentations completely miss. Hugh Everett III was a graduate student at Princeton in the mid-1950s. His thesis advisor was John Wheeler, one of the great physicists of the century, the man who coined the term black hole, and who bridged the gap between Einstein's general relativity and the quantum mechanics of the following generation. Everett's thesis, submitted in 1957, was titled Relative State Formulation of Quantum Mechanics, and it proposed a reading of quantum mechanics so radical that Wheeler spent considerable effort trying to get Everett to soften it before publication. Everett's insight was this: the measurement problem in quantum mechanics, the question of why quantum superpositions, which can in principle exist at any scale, always appear to collapse to definite classical values when we observe them, had been addressed by Bohr and Heisenberg through the introduction of an ad hoc rule called wave function collapse. When a quantum system is measured, the wave function collapses from its superposition to one of its basis states with a probability given by the square of the corresponding amplitude. This rule produces the right experimental predictions, but it is a rule without a physical basis. Nothing in the Schrödinger equation, which describes the smooth, deterministic, unitary evolution of quantum states, says anything about collapse. Collapse is added as an external postulate without derivation, without physical mechanism. Everett asked, what if collapse doesn't happen? What if the wave function always evolves unitarily, exactly as the Schrödinger equation says, with no collapse, with no external rule, with nothing beyond the smooth mathematical evolution of the quantum state? The answer, if you follow it carefully, is that the universe branches. When a quantum measurement occurs, when a qubit is measured and found to be in state 0 or state 1, what actually happens in Everett's picture is that the measuring device, and the experimenter, and the room, and everything entangled with the quantum system all enter into a superposition with it. The quantum state of the entire universe, the universal wave function, evolves to include all possible measurement outcomes, with the measuring device reading 0 in one branch and 1 in another, and the experimenter seeing 0 in one branch and 1 in the other. Both branches are equally real, equally existing, equally physical. From the experimenter's perspective within a branch, they see a definite outcome, because their version of the experiment, their version of the measuring device, is in a definite state within their branch. But at the level of the full wave function, both outcomes have occurred in separate, non-interacting branches of reality. This process happens constantly for every quantum interaction in the universe. The universal wave function has been branching since the beginning of the universe at every quantum event, accumulating a structure of staggering complexity, a vast branching tree of alternative histories, each one as real as every other one, each one populated by versions of every particle and field and planet and person and civilization that has ever existed. The number of branches is not 2, it is not millions, it is not billions, it is, quite literally or beyond enumeration, every quantum event in every atom, in every particle interaction, in every moment of cosmic history, branches the wave function. The number of branches of the universal wave function is incomprehensibly vast, far larger than the number of atoms in the observable universe, far larger than the number of moments of time since the Big Bang. It is a number so large that trying to state it as a finite integer is essentially meaningless. This is Everett's proposal. Not a metaphor, not a narrative device, a literal description of physical reality, derived from taking the Schrödinger equation seriously without adding any external rules. The universe is the wave function. The wave function branches without collapsing. All branches are real. Now, what does this mean for quantum computers? In Deutsch's interpretation of the many worlds framework, the one he developed in the 1980s and 1990s, and that he describes in his books, The Fabric of Reality and The Beginning of Infinity, a quantum computer is a machine that performs computation across multiple branches of the wave function simultaneously. The 9 quadrillion states of Sycamore's 53-qubit superposition are 9 quadrillion real, physical existing branches of the quantum state of the computer, each one performing part of the computation, all simultaneously. The interference between branches, the quantum mechanical interference that gives the algorithm its power, is a physical interaction between real computational processes happening in real, parallel branches of reality. When Sycamore completes its computation in 200 seconds, it is completing a computation that would have taken 10,000 years on the best classical computer in a single universe. It completes it so quickly because it is not working in a single universe. It is working in 9 quadrillion universes at once, each one performing part of the work, the results combined through quantum interference into the single answer that is read out when the qubits are finally measured. The answer emerges into our branch, your branch, the one you're reading this in, as a measurable classical result. The other 9 quadrillion branches of the computation collapse or decohere, their contributions having been absorbed into the interference structure that produced the output. From your perspective, you see one computer in one room producing one answer, but in the many worlds picture, what actually happened is that 9 quadrillion computations happened in 9 quadrillion parallel realities, and their results were woven together by quantum interference to produce the outcome you observe. This is Deutsch's answer to the question, where did the calculation take place? And it is not the answer of a man who enjoys shocking people, or who is being deliberately provocative. It is the answer of a man who has thought about the foundations of quantum mechanics and the theory of computation for 4 decades, and who believes that honest physics requires it. He has a specific challenge for anyone who rejects this answer. If the computation did not happen in other branches of the wave function, if it happened only in the physical qubits in California, then explain where the computational resources came from. 53 physical objects performed a computation that would have required the equivalent of 9 quadrillion classical processing operations in parallel. Either those 9 quadrillion parallel processes happened in some physical substrate, in which case you need to explain what that substrate is, or the computation was not physical, in which case you have a computational output that was not produced by any physical process, which is a contradiction. The Copenhagen response is, again, that the question of where the computation happened is not a well-formed physical question. The formalism predicts the output. The formalism is correct. The question of what physically produced the output beyond the formalism is not a physics question. Deutsch finds this response intellectually dishonest. It is a refusal to think, he has said in interviews. It is the answer of someone who has decided that the foundations of quantum mechanics are too uncomfortable to engage with, and has decided to call that discomfort a philosophical position. He is not entirely alone in this assessment. John Bell, who spent much of his career probing the foundations of quantum mechanics, and whose inequality we discussed in the last chapter, wrote extensively about the unsatisfying nature of the Copenhagen interpretation's refusal to address questions of ontology. He once wrote that the word measurement should be banished from the vocabulary of fundamental physics because it smuggled in a macroscopic classical concept at the heart of a supposedly fundamental theory. A theory of everything, he argued, should not have measurement as an undefined primitive. But many physicists, including many who have thought deeply about these questions, find the many worlds interpretation equally or more uncomfortable than Copenhagen for different reasons. And their discomfort is not mere squeamishness. It is based on specific, serious philosophical and physical objections that deserve a full hearing. Let's address the most important of them. Because the case for the many worlds interpretation is compelling, but it is not airtight. And the reason it is not airtight takes us into territory that is, in some ways, even stranger than the interpretation itself. The most serious objection to the many worlds interpretation is not the extravagance of the claim that there exist a vast number of parallel realities, each as real as ours. Physicists are generally willing to accept extravagance if the equations demand it. The serious objection is about probability. In the many worlds interpretation, every possible measurement outcome occurs in some branch of the wave function. This is the mechanism by which the theory avoids wave function collapse. Instead of one outcome occurring and others disappearing, all outcomes occur and no branch disappears. But this immediately creates a problem with probability. If all outcomes occur, why do we observe that some outcomes are more probable than others? When we measure a qubit that is in the superposition of state 0, with amplitude square root of 0.9, and state 1, with amplitude square root of 0.1, we observe state 0 90% of the time and state 1 10% of the time. In the many worlds picture, both outcomes occur. There is a branch where state 0 is observed and a branch where state 1 is observed. Why should we assign these branches different probabilities? This is the probability problem in Everett's interpretation, and it has been the central technical challenge for many worlds advocates for 60 years. If all branches are equally real, and all branches occur, what does it mean to say one outcome has a 90% probability? Probability of what? The best answer currently available, and it is genuinely good, mathematically rigorous, and advanced the subject significantly, is the decision theoretic approach developed by David Deutsch and David Wallace. They argue that the Born rule, the quantum mechanical rule that says probabilities are given by the squares of the wave function amplitudes, can be derived from rational decision theory in a branching universe, that any rational agent who knows they will branch at a quantum measurement and who wants to make optimal decisions about bets on the outcomes must assign probabilities proportional to the squared amplitudes. The Born rule is not an additional postulate of quantum mechanics, but a theorem derivable from the structure of the many worlds theory combined with rational agency. This is impressive work. The Deutsch-Wallace proof has been analysed, challenged, and refined extensively. Whether it fully solves the probability problem is contested. Some philosophers of physics find it compelling, others find specific gaps. But it represents the most serious attempt to address the most serious objection, and the fact that the objection can be engaged at this level of mathematical rigour is itself a mark of the interpretation's maturity. There is another objection that is less often discussed in technical terms, but that lands harder emotionally and conceptually than any of the mathematical ones. It is the objection from waste. In the many worlds interpretation, every time a quantum event occurs, every time a photon passes through a polarizer, every time a radioactive nucleus decays or doesn't, every time one of the 10 to the 26th atoms in your body undergoes a quantum interaction, the universe branches, multiple times, into states that will never interact again, that will never be combined or recombined, that exist in permanent isolation from each other from the moment of branching onward. The branch in which the photon was absorbed and the branch in which it was transmitted evolve forever in parallel, permanently separated, each carrying a complete history and a complete physical world. The sheer scale of this branching, happening every instant in every atom throughout the entire universe, throughout all of cosmic history, produces a number of simultaneously existing branches that is beyond any meaningful description. Not 9 quadrillion. Not 9 quadrillion times 9 quadrillion. A number so large that even the concept of a large number fails to capture it. The many worlds interpretation implies that the universe we can see and observe is an infinitesimally tiny fragment of the actual physical reality, that the observable universe, with its hundreds of billions of galaxies and its 10 to the power of 80 atoms and its 13.8 billion years of history, is a single branch in a structure so vast that no language has evolved to describe it. This is not metaphysics. This is the direct implication of taking the Schrödinger equation seriously, without addition or modification, as a complete description of physical reality. If the Schrödinger equation is right, and every experiment ever performed confirms its predictions without exception, and if the wave function describes something physically real, and if there is no physical collapse mechanism, then the many worlds interpretation follows as a logical consequence, and the scale of what it implies follows from the mathematics of how many times quantum events occur in the observable universe. There is a specific estimate worth dwelling on. The physicist Max Tegmark, who is one of the most prominent advocates for taking the wave function seriously as a description of a real branching multiverse, has estimated the branching rate of the universe. Every quantum event, every photon interaction, every electron transition, every radioactive decay, splits the universal wave function into new branches. The number of such events per second, across the 10 to the power of 80 particles of the observable universe, is incomprehensibly large. Tegmark's estimates suggest that the universe has produced something like 10 to the power of 10 to the power of 64 distinct branches since the Big Bang. This is not 10 to the power of 64. The superscript itself is 10 to the power of 64. It is a power tower, a number whose magnitude cannot be comprehended by any analogy drawn from everyday experience or even from the scale of the observable universe. The observable universe, with its hundreds of billions of galaxies and its 13.8 billion years of history, is one branch out of this unimaginable total. 1. The physical reality described by the many worlds interpretation is so much larger than the observable universe that the observable universe is not a significant fraction of it. It is not even a rounding error. It is nothing. A single thread in a fabric whose full extent exceeds all description. Physicists who are drawn to the many worlds interpretation often describe the experience of first fully accepting it as a kind of conceptual vertigo, a sense of the ground shifting permanently under your feet. Not a bad feeling, some of them say, but not a comfortable one either. Sean Carroll, the theoretical physicist at Johns Hopkins who has written extensively on many worlds and advocates for it, has said, "I think the universe branches all the time. I think there are an enormous number of copies of me and an enormous number of copies of everyone else. This is what the physics says. I've just decided to believe the physics." That last sentence, I've just decided to believe the physics contains more complexity than it first appears, because the physics does say this. That's not in dispute. The question is whether the wave function is literally real, or whether it is a mathematical representation of something that we don't yet have a complete theory for, or whether the whole framework of asking about the physical reality of the wave function is somehow misconceived. The quantum computer in California did not answer this question, but it made the question urgent in a way it had never been before. Because before Sycamore, you could argue that quantum computing was a theoretical possibility with no demonstrated advantage large enough to force the interpretation question. After Sycamore, after a physical machine performed a computation that is 10,000 years faster than the best classical alternative, the question of where the computational resources came from is not academic. It is a question about the engineering of a real system, a system that will be scaled up, made more powerful, put to work on drug discovery and optimization and cryptography and materials science. When we build a quantum computer with 1,000 qubits, something that is expected to be demonstrated within this decade, the superposition will contain 2 to the power of 1,000 components. That is a number with more than 300 digits. The number of atoms in the observable universe is a number with roughly 80 digits. A 1,000 qubit quantum computer will have a superposition size that exceeds the number of atoms in the observable universe by a factor that itself has more than 200 digits. Where is that computation happening? In the many worlds interpretation, in more parallel realities than we have atoms to represent the number. In the Copenhagen interpretation, the question is meaningless. In pilot wave theory, in a single universe, guided by a non-local wave that somehow contains all the information about all possible computational paths. Pick one, because you are living in a universe that now contains machines that make the choice of interpretation a matter of practical consequence, not merely philosophical preference. The machines are getting larger, and as they scale, the question of where the computation is happening grows proportionally harder to ignore. And there is one more layer to this that we have not yet addressed. The layer that connects the abstract interpretation debate to the specific, physical, engineered fact of how quantum computers actually function without collapsing into classical noise. The layer that tells you why Sycamore had to be cooled to 15 millikelvin, why the qubits had to be isolated with extraordinary care from any contact with the environment, why the entire apparatus was designed around a specific, profound, and deeply underappreciated problem in quantum mechanics that sits at the heart of the interpretation question. That problem has a name: decoherence. And understanding it is essential to understanding what quantum computers are really telling us about reality and what they cannot tell us yet. But that is the story of the next chapter. End of part 1, continuing in part 2, chapters 4 through conclusion. Chapter 4, Decoherence, the reason the universe hides. It's branching from you. Here is the thing that makes quantum mechanics uniquely infuriating to think about seriously. The quantum world is right here, underlying everything, operating in every atom in your body, in every photon hitting your retinas, in every electron flowing through the circuits of the device you're watching this on. It is not in some remote laboratory, or at the bottom of a particle accelerator, or in the special conditions of outer space. It is the bedrock of physical reality, always and everywhere active, always and everywhere present. And you cannot see it. You cannot see a superposition with your eyes. You cannot feel a quantum branch with your hands. You cannot walk into a hardware store and buy a device that reveals the quantum nature of the world around you. Not because quantum effects are subtle or weak. They are not in the sense of being real and determinative of all macroscopic outcomes, but because the process called decoherence makes the quantum nature of the world effectively invisible at the scales we inhabit. Understanding decoherence is understanding why the world looks classical, even though it is quantum. And it is the thing that the engineers of Sycamore spent most of their engineering effort fighting. Let's define it clearly. Decoherence is what happens when a quantum system interacts with its environment, and in the real world, everything interacts with everything else constantly. Air molecules bounce off surfaces, photons scatter off particles, electromagnetic fields permeate every volume of space. Heat is nothing but the random quantum mechanical interactions of countless particles. Every quantum system, at room temperature in normal conditions, is in constant chaotic interaction with a vast environment. When a qubit in superposition interacts with its environment, with a single air molecule with a stray photon, with a fluctuating magnetic field from a nearby wire, the superposition doesn't immediately collapse. What happens is more subtle and in many ways more profound. The qubit becomes entangled with the environment. Its quantum state, the superposition of 0 and 1, gets absorbed into a vastly larger superposition that includes the qubit and the interacting environmental particles. The local superposition of the qubit spreads out into the environment, diluting into the enormous number of degrees of freedom of the thermal surroundings. Once this happens, the interference between the components of the qubit's superposition, the interference that is the source of all quantum computational power, effectively disappears. Not because the branches of the superposition have collapsed or gone away, but because the interference terms in the combined qubit environment state are averaged over the random thermal fluctuations of the environment, and they wash out to 0. The superposition is still there, in principle, spread across the qubit and the environment. But the quantum coherence, the capacity for the components of the superposition to interfere with each other, has leaked out into the environment and is gone from the qubit's perspective. This is why your brain, despite being made of quantum mechanical atoms, does not exhibit quantum superposition at the neural level. A neuron in your brain is constantly interacting with trillions of surrounding molecules in warm, wet, noisy, biological tissue. Any quantum superposition in a neuron decoheres in femtoseconds, 10 to the power of minus 15 seconds, a millionth of a billionth of a second, far faster than any neural process operates. By the time any neuron fires, every quantum superposition that might have existed in its atoms is long gone, lost to decoherence into the surrounding thermal bath. Your brain is, at its operational level, classical. Not because quantum mechanics doesn't apply to it, but because the environment destroys quantum coherence faster than any coherence can be exploited. The decoherence timescales are worth spelling out concretely, because they reveal something about why building quantum computers is one of the most precise engineering challenges ever undertaken. A superconducting qubit at room temperature, if you just sat the chip on a table without cooling it, would decohere in picoseconds, 10 to the power of minus 12 seconds, essentially instantaneously from an engineering perspective. At cryogenic temperatures of 4 Kelvin, the decoherence time extends to microseconds. At 15 millikelvin, the operating temperature of Sycamore, the best qubits achieve coherence times of up to 100 microseconds, sometimes reaching the millisecond range. 100 microseconds sounds brief, but for a quantum processor running microwave gate operations at gigahertz speeds, 100 microseconds contains thousands of computational operations. It is enough to run a meaningful quantum circuit before the coherence is destroyed. The race in quantum computing engineering is fundamentally a race to extend coherence times while reducing gate error rates. Every improvement in coherence is an improvement in how long the quantum superposition can be maintained, how long the branches of the computation can be held together, coherently interfering, before decoherence separates them irreversibly. From the many worlds perspective, engineering better quantum computers is literally the project of holding open more branches of reality for longer, exploiting their parallel computational capacity before the environment forces the branching to become permanent and non-interfering. From the Copenhagen perspective, it is the project of maintaining precise quantum mechanical evolution, long enough to extract the probabilistic output correctly predicted by the formalism. Both descriptions are physically accurate at the operational level. They diverge only on what it means. This is also why building quantum computers is so hard. To maintain the quantum coherence of the qubits long enough to perform a computation, you must isolate them from the environment with extraordinary thoroughness. Sycamore's qubits are cooled to 15 millikelvin, a temperature colder than the coldest known regions of outer space, which are around 2.7 Kelvin, the temperature of the cosmic microwave background. At 15 millikelvin, thermal fluctuations are suppressed to the point where they interact with the qubit slowly enough that the computation can be completed before decoherence destroys it. The entire apparatus, the dilution refrigerator, the shielding, the carefully designed qubit geometry, the microwave control lines, is an engineering project whose central purpose is to delay decoherence long enough to compute. This fact, that quantum computers require such extraordinary isolation from the environment, is itself a profound statement about the nature of reality. it says that the quantum world is fragile. Not fragile in the sense of being weak, but fragile in the sense that the quantum features of a system, its superposition, its coherence, its capacity for quantum interference, are easily destroyed by contact with anything outside the system. The environment is a decoherence machine. It destroys quantum coherence ruthlessly and relentlessly, converting every quantum superposition it touches into something that looks, from the perspective of anyone examining only the qubit, like classical randomness. Now, what does decoherence mean for the interpretation of quantum mechanics? In the many worlds interpretation, decoherence is the mechanism by which branches separate and become non-interacting. When Sycamore's qubits decohere at the end of a computation, when the final measurement is made and the classical result is extracted, what is happening in the many worlds picture is that the quantum state of the computer becomes entangled with the measuring apparatus, which becomes entangled with the environment, and the different branches of the quantum state separate into macroscopically distinct, non-interfering branches of the universal wave function. The branch in which qubit 1 is 0 and qubit 2 is 1 and qubit 3 is 0 and so on, that branch evolves separately from the branch in which the qubits are in a different configuration. The branching that was already happening at the quantum level, inside the computation, becomes permanent and macroscopically visible at the moment of measurement. Crucially, decoherence does not cause wave function collapse. This is a common misunderstanding. Decoherence explains why quantum superpositions become effectively invisible at large scales, why we never see Schrödinger's cat alive and dead simultaneously, without requiring wave function collapse. In the many worlds picture, the cat is in a superposition of alive and dead after the quantum event. Decoherence entangles the cat with the room with the building with the planet. The alive cat branch and the dead cat branch become macroscopically distinct and non-interfering. Each branch contains an observer who sees a definite classical outcome, but both branches are real. Decoherence made them non-interfering, not non-existent. In the Copenhagen picture, decoherence is sometimes presented as a resolution of the measurement problem, as the physical mechanism by which wave function collapse effectively occurs. But this is philosophically unsatisfying. Decoherence explains why superpositions become effectively undetectable at macroscopic scales. It does not explain why, at the moment of measurement, one definite outcome occurs rather than another. It does not explain why the probabilities are what they are. It explains why you can't see the superposition. It does not explain what physically happens to make you see one outcome rather than all of them. This is the point on which the Copenhagen and many worlds interpretations most clearly diverge, and it is also the point most directly relevant to the engineering reality of quantum computing. For Sycamore to work, its qubits must remain coherent during the computation. The isolation from the environment is the engineering implementation of keeping the branches of the computation from prematurely separating. The qubits in superposition are threads of multiple branches of the quantum state held together, coherently interfering for the duration of the computation. When the measurement is made, the branches separate and the result enters the macroscopic classical world. In the many worlds interpretation, this means that at the moment of measurement, you, the observer reading the result as branch. There is now a version of you who read result A and a version of you who read result B, each in a distinct branch of the universal wave function, each experiencing a definite classical outcome. Both are you in some meaningful sense, both are equally real in the physics. Only one is you from the inside of any given branch. Every time you read the output of a quantum computation, in the many worlds picture, you split. The measurement event creates new versions of you in new branches of reality. This happens so fast, so constantly, and so completely invisibly to anyone within a branch that there is no moment at which you can directly perceive the branching. But the branching in this picture is the most fundamental physical event, more fundamental than particle collisions or gravitational interactions or the emission of light. It is the universe's basic process of becoming, the mechanism by which reality diversifies into everything that can happen. Whether or not this is what actually happens, it is what the equations say happens if you take them literally, and the quantum computer in California is the clearest demonstration yet that the equations are right. Chapter 5. The Rivals, Copenhagen, Pilot Wave, and the physicists who think parallel universes are the wrong answer. It would be unfair, and it would also be poor science communication, to present the many worlds interpretation as the inevitable conclusion and leave the objections as footnotes. The debate is real, ongoing, and populated by serious people with serious arguments. Let's give those arguments their full weight. The Copenhagen interpretation, as I've described it, is sometimes characterized as a refusal to answer the deep questions. This characterization is somewhat unfair to Bohr, who was genuinely wrestling with profound questions about the relationship between quantum phenomena and classical description. Bohr's view was not simply shut up and calculate. It was a considered philosophical position, roughly that the quantum world cannot be described independently of the classical apparatus used to measure it, that the boundary between quantum and classical is fundamental and irreducible, and that attempts to describe the quantum world as it is in itself, independent of measurement, are category errors. This is a defensible philosophical position. It draws on a tradition in philosophy of science going back to Kant. The idea that our access to reality is always mediated by our cognitive and instrumental apparatus, and that asking about what is really there, independent of any possible observation, is asking a question that cannot, even in principle, be answered. Bohr was, in a sense, drawing a principled philosophical line around the question of quantum reality and saying, this question is not one that physics can or should answer. The problem with this position, in the era of quantum computers, is that quantum computers are classical outputs of quantum computations. The result that comes out of Sycamore is a classical bit string, a definite sequence of zeros and ones that can be read, stored, transmitted, and verified. That classical output was produced by a quantum process. To say that the quantum process cannot be described in itself, independent of the classical measurement that extracted the output, is to say that the physical process that produced the computation cannot be described physically. Which is to say that the most powerful computation in the history of human technology was produced by a process that physics, by design, refuses to describe. This is hard to accept as anything other than an admission of incompleteness. The pilot wave interpretation, formulated by Louis de Broglie in 1927 and independently rediscovered and developed by David Bohm in 1952, takes a completely different approach. It preserves the single universe. In the pilot wave picture, particles are real, have definite positions at all times and move along definite trajectories. The quantum weirdness is not located in the particles themselves, but in the pilot wave, a physical wave that propagates through all of space, guides the motion of the particles, and encodes all of the quantum statistical predictions. In the pilot wave interpretation, the qubits of Sycamore are real, classical objects with definite configurations at every moment. They move along definite trajectories guided by the pilot wave. The quantum computation happens because the pilot wave is sensitive to the full quantum state. It incorporates information about all possible configurations of the qubits, not just the actual one, and its guidance of the actual qubit trajectory effectively searches through the configuration space in a way that exploits this global information. This is a genuinely different ontology from many worlds, and it has real virtues. It preserves a single universe. It gives particles definite positions. It has no measurement problem. Measurement is just the reading of a definite value that the particle always had. The only thing it requires beyond standard quantum mechanics is the pilot wave, and the postulate that particle positions are always definite and always distributed according to the quantum mechanical probability distribution. The cost is non-locality. The pilot wave guides each particle based on the configuration of all other particles in the system, instantaneously, regardless of distance. When Sycamore's qubits interact, the pilot wave that guides each of them depends on the positions of all of them, non-locally and instantaneously. This non-locality is technically hidden. It cannot be used to send signals faster than light, because the probabilities work out to be the same as in standard quantum mechanics. But it is a fundamental non-local ontology. The pilot wave knows at every instant the positions of all particles everywhere in the universe. This is not modest. A wave that extends over all of space, instantaneously sensitive to the positions of every particle, is an extraordinarily rich and complex physical object. It requires a configuration space, the space of all possible positions of all particles in the universe, as a fundamental physical arena. That space has an astronomically large number of dimensions. 3 dimensions per particle summed over all particles in the universe. The pilot wave lives in this space, not in ordinary 3-dimensional space. This is an ontological commitment that many physicists find at least as extravagant as parallel universes, and perhaps more so, because it requires a fundamentally new kind of physical object, the pilot wave in configuration space, rather than just more instances of the objects we already know: particles, fields, universes. There are other interpretations. Cubism, quantum Bayesianism, holds that the wave function represents an agent's beliefs about measurement outcomes, not a description of physical reality. There is no collapse because there was never a physical wave function. There was only a probability assignment, and updating probability assignments isn't a physical event. This is a radical anti-realist position, and it is internally consistent, but it raises the question of what quantum mechanics is a theory of, if not of physical reality. Cubism's proponents have responses to this question, but it remains deeply controversial. There is also a class of interpretations that take a different approach entirely. Instead of accepting the Schrödinger equation as complete and asking what it means, they propose modifications to the Schrödinger equation that physically cause wave function collapse. These are called spontaneous collapse theories or objective collapse theories, and the most developed of them is the GRW theory, named after Girardi, Rimini and Weber, who proposed it in 1986. In GRW, the Schrödinger equation is modified by adding random spontaneous collapse events that hit individual particles with a very small rate, about once every 10 to the 10th power seconds per particle. For a single particle, this is negligible. The particle almost never collapses spontaneously, but for a macroscopic object containing 10 to the 26th power particles, the combined rate of spontaneous collapses is enormous, and the object effectively collapses to a definite classical state almost instantaneously. GRW has the virtue of explaining the classical appearance of the macroscopic world without requiring an observer or a measurement. Collapse happens because the modified Schrödinger equation contains a collapse mechanism. It is a physical process, not a postulate or an interpretation. This is clean and philosophically satisfying in a way that Copenhagen is not. The cost is that GRW makes different predictions from standard quantum mechanics for systems containing very large numbers of particles that are maintained in superposition for extended periods. Specifically, it predicts a very slow, very small decoherence due to the spontaneous collapse events. For small, well-isolated quantum systems, the predicted deviation is too small to be currently measurable. But for large quantum systems, including specifically quantum computers with many qubits, the GRW decoherence rate might eventually be detectable as an anomalous decoherence source that cannot be explained by environmental interactions. This means GRW is, unlike Copenhagen and many worlds, potentially distinguishable from standard quantum mechanics by experiment. If quantum computers scale to millions of error-corrected qubits, and if the decoherence rates in those systems are measured with sufficient precision, the presence or absence of the GRW spontaneous collapse contribution could in principle be detected. If GRW is right, there should be a floor to the decoherence rate, a minimum rate that cannot be reduced by better engineering because it comes from the fundamental physics of the modified Schrödinger equation. If many worlds is right, there should be no such floor. These predictions are different and, as quantum hardware improves, could become experimentally distinguishable. This is one of the few examples where the interpretation debate has crossed into empirical testability, and it is one of the reasons why the development of large-scale quantum computers is scientifically important beyond their computational applications. They are, simultaneously, a technology and a laboratory for testing the foundations of quantum mechanics in regimes that have never been experimentally accessible. Relational quantum mechanics, developed by Carlo Rovelli, holds that quantum states are relative to observers, that different observers can consistently assign different quantum states to the same system, and that there is no universal quantum state, only relational ones. This is an intriguing approach with deep connections to the relational nature of space-time in general relativity, but it requires abandoning the idea of an observer-independent reality in a way that many physicists find unacceptably radical. The point is not that any one of these interpretations is obviously correct and the others obviously wrong. The point is that this is a live, unresolved debate among serious scientists, and that the resolution of this debate matters in a way that goes beyond academic philosophy. Here is what all interpretations agree on. The mathematical formalism of quantum mechanics is correct, All interpretations except the Schrödinger equation, the Born rule, derived or postulated, and the full experimental record of quantum mechanics, including the Bell inequality violations. They differ on what the formalism means, on the ontological status of the wave function, on whether there is a single universe or many, on whether particles have definite positions at all times, on whether observers are special. And here is what none of them can currently tell you: which one is right. Not because we haven't tried, because the interpretations carefully constructed are designed to reproduce exactly the same experimental predictions. They're empirically equivalent at every observable level. There is no experiment you can do with any currently available technology that would distinguish between many worlds and pilot wave, or between Copenhagen and relational quantum mechanics. The debate is, in a specific and frustrating sense, beyond the reach of current experimental physics. This is why many practicing physicists prefer not to think about it. If you're calculating a scattering amplitude for particle physics, the interpretation question is irrelevant. If you're designing a quantum circuit for quantum computing, the interpretation question is irrelevant. The formalism gives you the answers you need. What the formalism means, physically, is a question you can safely table until it matters. The reason it is starting to matter, the reason the Sycamore result has sharpened this debate, is that it matters for how we understand the limits and possibilities of quantum technology. If many worlds is right, the computational resources of a quantum computer grow without bound as the number of qubits increases, because more qubits mean access to the computational capacity of more parallel branches. If Copenhagen is right, questions about the origin of those resources are not physical questions. If pilot wave is right, the resources come from the global, non-local structure of the pilot wave in configuration space. Each answer has different implications for what quantum computers are, what they can ultimately do, and what the universe is fundamentally like. Chapter 6. The terrifying implication. If many worlds is right, you're not alone. Let's take many worlds seriously for a moment, not as a philosophical abstraction, as a description of physical fact. Let's follow it where it goes. If the many worlds interpretation is correct, if the wave function is real, if it branches without collapsing, if all branches are equally physical, then the following is true right now as you read this. There is a version of you who made a different choice this morning, a different version who chose a different job 5 years ago, a different version who was born in a different country, raised in a different language, developed different ideas, holds different beliefs, not as a hypothetical, not as a what if, as a physical fact about the contents of the universe, the full universe, the one described by the wave function, not just the branch you happen to be in. There are versions of you who are, by any measure you care to apply, unrecognizably different from you. Versions who survived accidents that killed you in your branch, versions who died in accidents that you survived, versions who never existed because the specific quantum event that led to the particular sperm and egg that created you came out differently in their branches. Every possible genetic combination that the quantum mechanics of your parents' biology allowed, every one of those combinations exists in some branch, each one as a real person as you are. The scale of this should stop you for a moment. We're not talking about a few parallel versions. We're talking about a number of versions of you, and of everyone who has ever lived, and of everyone who has never lived but could have, that exceeds any number with a name. The universe, in the many worlds picture, is not just large. It is not just very large. It is populated by a plenitude of physical reality that contains, as one of its branches, everything that has ever happened and, in other branches, everything that could have happened but didn't. And here is what makes this specifically, viscerally strange in the context of quantum computers. When Sycamore performed its computation in 200 seconds, it did so by exploiting the computational resources of a subset of those branches. Not all branches. The computational resources of one 53-qubit quantum system in a single run of a quantum algorithm are enormous but finite. But the mechanism by which the machine accessed those resources is the same mechanism by which the universe, in the many worlds picture, branches at every quantum event in every atom. The machine is not doing something fundamentally new. It is harnessing, in a controlled and engineered way, the same physics that has been branching reality since the Big Bang. It is the first machine deliberately designed to exploit the parallel nature of reality, if reality is, in fact, parallel. This connection between the quantum computation and the branching universe is what makes the Sycamore result philosophically significant beyond its computational achievement. It is not just that a fast computation was performed, it is that the mechanism of the fast computation is the same mechanism that, in the many worlds interpretation, produces the full structure of reality. Understanding quantum computers means understanding, or at least confronting, the question of what reality is. But there is a specific implication of many worlds that most popular treatments of the interpretation fail to address, and it is the one that should genuinely give you pause. In the many worlds picture, every decision you make is split. Not in a metaphorical sense, not in the sense of wondering about the road not taken. Literally split. Every quantum event that influences your decision-making process, and your brain is full of quantum processes. The thermal fluctuations of ion channels, the quantum mechanics of photoreception in your eyes, the quantum chemical processes of neurotransmitter binding. Every one of those quantum events branches the wave function. The you who did one thing and the you who did another thing are both equally real, both equally physical, both equally existing in branches of the universal wave function that are from this moment forward permanently separated. The moral and philosophical implications of this are ones that philosophers have been wrestling with since Everett's paper was published, and they have not reached consensus. Does it make sense to feel regret if every choice you didn't make was made by another version of you that is equally real? Does it change the weight of a moral decision, knowing that in another branch you will make the other choice? Does personal identity survive branching? Are the two post-decision versions of you both you, or has the branching created two new people, each of whom has a reasonable claim to continuity with the pre-decision you? These questions are not rhetorical. They are genuine open problems in philosophy of mind and personal identity, and the answers depend in part on what you think personal identity consists of, which is itself a deep and unresolved question. But the questions are forced on us by the physics, not by speculation, not by science fiction, but by following the equations without flinching. Some philosophers and physicists who accept many worlds have proposed that the branching structure of the wave function actually enriches our moral framework rather than undermining it. In a single universe picture, making a decision closes off all other possibilities permanently. In a many worlds picture, making a decision creates branches. The other possibilities are not closed off. They are realized by versions of you who made different choices. This could be seen as liberating. Nothing is truly irreversible at the level of the wave function, but it could also be seen as diluting moral responsibility. If the version of you who made the wrong choice also exists and is equally real, what is the meaning of having made the right choice? Derek Parfit, the philosopher who spent his career on questions of personal identity and who wrote the landmark philosophical text, Reasons and Persons, argued at length that our intuitive notion of personal identity is philosophically incoherent even in a single universe picture, and that the branching implied by many worlds simply makes more explicit the ways in which identity already fails to be what we think it is. Parfit, who was not a physicist but who engaged seriously with the philosophical implications of quantum mechanics, found the many worlds picture congenial to his own deflationary view of personal identity. The self is not a special, persistent object, but a pattern of physical and psychological continuity that can fork, merge, and overlap in ways that have no clean description in terms of same person or different person. If Parfit is right, then the branching of the wave function is not a metaphysical catastrophe, but a confirmation of something philosophers should have known anyway, that the boundaries of the self are not sharp, that personal identity over time is a useful fiction rather than a metaphysical fact, and that the correct response to finding yourself in one branch of the wave function is neither despair nor consolation, but something more like equanimity at the recognition that the universe does not single you out for any special treatment. You are a pattern in a branch. Other patterns in other branches are you in every relevant physical sense. The universe does not privilege any branch over any other. It holds them all simultaneously in the wave function, equally real, equally indifferent. There is also a specific implication for the status of the present moment. In the many worlds picture, the present moment is not a feature of the universe. It is a feature of a branch. In your branch, this is now. In another branch, something different is now. A different configuration of particles, a different experienced reality, equally now from inside that branch. There is no cosmic present that encompasses all branches. Each branch has its own present, equally real, equally experienced from the inside. The universe, the full physical universe, the one described by the wave function, does not have a single now. It has an unimaginably vast number of nows, each one as real as every other one, each one the now of the version of reality that exists in that branch. This is by any measure a staggering conclusion. It goes far beyond the already staggering claim that parallel realities exist. It says that the concept of the present moment, the concept that seems most immediate, most undeniable, most bedrock in all of human experience, is branch relative. You're not in the present of the universe, you're in the present of your branch. Physicists who accept many worlds sometimes describe the experience of internalizing this implication as a second wave of conceptual vertigo, different from the first wave of accepting the existence of parallel branches. The first wave is about size. The universe is vastly bigger than you thought. The second wave is about location. You're not where you thought you were. You're not in the universe. You're in a branch of the wave function. Chapter 7. What the machines are actually telling us. Let's step back from the philosophical depths and ask the question that should be asked about any theoretical framework. What does it predict? What experimental evidence, if any, bears on whether many worlds or some alternative is correct? And what are quantum computers as they scale up actually going to tell us? The frustrating answer is that the interpretations were specifically constructed to be empirically equivalent. They all predict the same outcomes for every experiment that can currently be performed. But this equivalence may not be permanent. There are specific proposals for experiments that could, in principle, distinguish between interpretations, and some of them are coming within reach. The most discussed is the quantum cognition proposal. In the many worlds picture, the superposition of the quantum computer is real and physical, and the interference that makes it computationally useful is physical interference between real branches. If this is true, then sufficiently large quantum superpositions should, in principle, be observable in macroscopic systems, not just in engineered quantum computers, but in biological systems, in materials, in any physical system where decoherence is sufficiently suppressed. Recent experiments in quantum biology have found evidence of quantum coherence in photosynthesis, in bird navigation via quantum effects in cryptochrome proteins, and in other biological processes. None of these constitutes evidence for many worlds specifically, but they establish that quantum superpositions can survive in warmer, noisier environments than was previously thought. More directly relevant are proposals for quantum gravity experiments. In 2017, Sugato Bose at University College London and Vlatko Vedral at Oxford proposed an experiment called the Bose-Marletto-Vedral (BMV) experiment that would attempt to detect quantum entanglement generated through gravitational interaction between two tiny masses placed in superpositions of positions. If the masses become entangled through gravity, it would provide evidence that gravity is a quantum force, that gravitons exist, and that the gravitational field can be in a superposition. This experiment doesn't directly test many worlds, but it tests the quantum nature of space-time, which is a prerequisite for any complete quantum interpretation. The experiment is technically demanding. It requires masses of about a microgram in superpositions with separation of about a micrometer, maintained for about a second, but it is within the reach of the next generation of matter wave interferometry. Several groups are actively working toward it. There is also a more speculative but fascinatingly direct proposed test of many worlds, the quantum suicide/quantum immortality thought experiment. In this proposal, a measurement is made on a quantum system in superposition. In one branch, the outcome is lethal to the experimenter, in the other, it is safe. If many worlds is correct, both branches occur, and the experimenter, from the inside of their subjective experience, always finds themselves in the branch where they survive. An observer repeatedly performing this experiment would accumulate evidence from their own first-person perspective for quantum immortality, surviving sequences of potentially lethal quantum events with probability that grows exponentially smaller with each repetition, explainable within the single universe framework as extraordinary luck, but explainable within many worlds as the simple fact that the observer's consciousness always continues in the branch where they survive. This is not an experiment anyone is proposing to actually perform, for obvious reasons. But the logical structure of the argument reveals something important. The many worlds interpretation has distinctive implications for the relationship between objective probability and subjective experience, and these implications are, in principle, testable, just not in ways that are humanely accessible. What quantum computers are actually going to tell us, as they scale, is something more pragmatic and more immediate. They are going to tell us about the practical limits of quantum computation, about decoherence, error correction, the relationship between circuit depth and noise. These are engineering facts, and they will be discovered whether or not we ever resolve the interpretation debate. But they will also tell us something about the nature of quantum computational resources in a way that is, at least in principle, interpretively significant. In 2023, IBM demonstrated a 1,121 qubit quantum processor called Condor, and more significantly, demonstrated a 133 qubit processor called Heron with dramatically lower error rates than its predecessors. The same year, IBM researchers published a landmark result in Nature showing that for a specific class of problems, their quantum processor produced results that were more accurate than any classical simulation they could run, a result they called utility-scale quantum advantage, distinct from the more narrow quantum supremacy demonstrated by Sycamore in 2019. The problem chosen was deliberately one with physical significance, a simulation of a quantum spin model relevant to condensed matter physics, and the results were verified against independent classical benchmarks in the regime where those benchmarks were tractable. This 2023 IBM result is, in some ways, more significant than Sycamore's 2019 result for the philosophical question. Random circuit sampling, Sycamore's task, was designed to demonstrate computational advantage without producing anything useful. The IBM result produced physically meaningful output, answers about the behavior of a real quantum mechanical system, using the quantum computer as a tool for physics, not merely as a benchmark. When a quantum computer correctly simulates a quantum system, the question of where the computation happened is not merely a question about where the numbers were crunched. It is a question about what physically performed the simulation of the quantum system, what executed the quantum dynamics that produced the correct answer. And the answer, in the many worlds picture, is that the dynamics were executed across the full superposition of the computer's qubits in all of their branches, simultaneously, the interference between branches producing the correct answer for the physical system being simulated. If quantum computers scale as expected, if the computational advantage grows exponentially with the number of qubits, if 1,000-qubit and million-qubit systems perform computations that are exponentially faster than any classical alternative, this is consistent with many worlds and inconsistent with any interpretation that doesn't somehow explain where the exponentially large resources come from. The Copenhagen response, the resources don't come from anywhere because the question is ill-formed, becomes increasingly strained as the systems scale. A machine that performs, in seconds, computations that would take the age of the universe on any classical computer is a machine that is doing something that requires explanation. The formalism gives the right answers is less and less satisfying as an explanation when the formalism is describing the behavior of systems that exist in your lab, in your city, on your planet. There is also a specific class of computation, quantum simulation, that makes the interpretation question most directly relevant. Richard Feynman's original motivation for quantum computing in his 1982 paper that first proposed the concept was the simulation of quantum systems. Classical computers cannot efficiently simulate quantum systems because the state space grows exponentially with the system size. A quantum computer can simulate a quantum system efficiently because it is itself a quantum system. The simulation is performed by mapping the target system's quantum degrees of freedom onto the computer's qubits and evolving them according to the appropriate Hamiltonian. When a quantum computer simulates, say, a large molecule for drug discovery, mapping the electrons and nuclei of the molecule onto the computer's qubits, and calculating the molecule's ground state energy, what it is doing, in the many worlds picture, is conducting the simulation across a vast number of parallel branches simultaneously, each branch representing a different configuration of the molecule, the interference between branches producing the correct ground state energy as the output. The power of quantum simulation is precisely the power of accessing the computational resources of those parallel branches. In the Copenhagen picture, the simulation is a sequence of quantum operations whose outcome is correctly predicted by the formalism, and the question of what physically happens during the simulation is not a physics question. But for the chemist who uses the output to design a drug that saves lives, the question of what made the computation possible is not purely academic. The answer shapes how they think about what the computation is, what it is doing, what its limits are. This is where quantum computers, as they scale from Sycamore's 53 qubits to the thousands and eventually millions of error-corrected qubits that are the goal of the industry, will force the issue, not by directly answering the interpretation question that may require experiments outside quantum computing, but by making the question impossible to avoid by presenting a technology whose capabilities outstrip any classical explanation, by demonstrating repeatedly and at larger and larger scales that there is something going on in a quantum computer that does not fit in any single universe picture without extraordinary auxiliary assumptions. The question asked at the beginning of this video, where did the calculation take place, will not become easier to dismiss as the calculations become larger. It will become harder. And the physicists who have been wrestling with it since 1957, since Everett first put it in print, will find themselves increasingly in the centre of conversations that used to seem abstract and now seem urgently practical. Conclusion. In October 2019, a machine in California performed a calculation in 200 seconds that would have taken the world's best classical computer 10,000 years. The engineers who built it could explain in full technical detail exactly how it worked. They understood the qubits, the gates, the error rates, the cooling requirements, the measurement scheme. They understood everything about the engineering. And in the years since, the machines have gotten larger, more precise, more powerful. IBM's 1121 qubit processor in 2023, Google's roadmap toward fault-tolerant quantum computing with millions of error-corrected logical qubits, Microsoft's topological qubit program, pursuing a fundamentally different qubit architecture based on non-abelian anyons, quasi-particles whose existence was itself predicted by quantum mechanics, and whose discovery in condensed matter systems won Nobel Prize recognition. The field is not slowing, it is accelerating. The computational advantage demonstrated by Sycamore is the first proof of concept for a technology that is only now entering the phase where it will produce applications, where the quantum advantage will translate from benchmark demonstrations to actual useful computation. And as the machines grow larger, the question that Sycamore first forced into focus will not go away. It will get louder. Because each additional qubit doubles the superposition. Each additional qubit doubles the question. At 53 qubits, you can perhaps still tell yourself the question is abstract, the computational advantage is impressive but not mind-bending, the physics is exotic, but the implications are speculative. At 1,000 qubits, you cannot. At 10,000, you cannot. At 1,000,000 fault-corrected logical qubits, performing computations that span state, spaces of 2 to the power of 1,000,000, a number that exceeds any physical quantity ever measured in the history of science by hundreds of orders of magnitude, you cannot tell yourself the question is academic. What did that calculation take place? The answer that the honest physics gives you is not comfortable. It is not reassuring. It does not end with a clean moral or a tidy resolution. It ends with a question about the size and structure of reality that has been sitting inside the equations of quantum mechanics since 1925, and that we have been collectively pretending was a philosophy problem rather than a physics problem for 100 years. It ends with the recognition that the machine in California, the one in the cold storage room, the one cooled to 15 millikelvin, the one that looks like a chandelier of gold and copper tubes hanging in a laboratory, is the most direct physical probe of the foundations of reality ever built, not because of what it computes, because of what it must be, physically, to compute it, because of what the universe must be, physically, to allow it to compute it. The machines are getting larger, the question is getting louder. The answer, when it comes, if it comes, will not be announced in a press conference about technological supremacy, or encryption threats, or the quantum computing race. It will be announced quietly in the foundations of physics literature, in a paper that most people will not read, that will describe an experimental result that changes the question from which interpretation is philosophically preferable to which interpretation the universe actually implements. That paper has not been written yet, but the machines that will make it possible are being built right now in laboratories in California and New York and Delft and Zurich. And the question they are being built, in part, to answer is the one that has been waiting for 100 years. Where is the calculation happening? What they did not answer, what the press conference did not cover, what the Nature paper did not address, what the world did not ask, was the question that sits beneath the engineering. The question that you cannot answer without taking a position on the deepest, most contested, most consequential debate in the foundations of modern physics. Where did the calculation happen? If you follow the physics honestly, the answer is one of three things. The calculation happened in other universes, in a number of parallel branches of the wave function too large to represent meaningfully, and the universe is a vastly, incomprehensibly larger structure than anything we observe, branching constantly, everywhere, at every quantum event, into realities as real as yours that you will never see and can never reach. Or the question of where the calculation happened is not a physical question, and physics is, at its foundations, deliberately incomplete about the physical reality it describes. Or the calculation happened in a single universe, guided by a non-local wave that instantaneously spans all of space and encodes the configuration of every particle in the universe in a configuration space of incomprehensible dimensionality. There is no fourth option that has been mathematically formalized and empirically tested. There is no comfortable answer. Each answer requires accepting something about reality that is profoundly alien to ordinary human intuition, each in a different way. David Deutsch believes the first answer, not as a working hypothesis, not as a useful model, as the truth. He has said, "The fact that single particles can behave as if they were somewhere else as well, and the fact that I can build computers that exploit that, is direct evidence that parallel universes exist." He has been saying this for decades. He was saying it before quantum computers existed as physical machines, and now physical machines exist that, in his reading of the physics, perform computations that can only be explained by resources spread across those parallel universes. Whether he is right, we cannot currently determine by experiment. But the question is not merely philosophical. It is a question about the structure of reality, about whether the universe you're in is the universe, or a branch, or a single trajectory through a higher dimensional space that contains all trajectories simultaneously. It is a question about the meaning of the present moment, of personal identity, of the nature of possibility and actuality. It is a question that quantum mechanics in the 1920s forced onto physics without warning and has never answered to anyone's complete satisfaction. And now we have built machines that make the question more urgent. Machines that, if they work as well as they are beginning to work, that, as they scale from 53 qubits to 1,000 to 100,000 to millions, will perform computations so far beyond any classical explanation that the silence on the question of where they are computing will become increasingly difficult to maintain. The engineers will keep improving the machines, the algorithms will keep getting better, the applications, drug discovery, material science, optimization, cryptography, will become real and commercially significant, and will change the world in ways that have nothing to do with the foundational question. But the foundational question will still be there, underneath every quantum computation, underneath every qubit in superposition, underneath the cold storage room in California, and every room like it that will be built in the coming decades. Where is the calculation happening? The answer, depending on who is right, is either that physics refuses to say, which is a kind of answer that should disturb us about the state of our most fundamental theory, or it is that the calculation is happening everywhere, in every branch of a wave function that has been branching since the first quantum event after the Big Bang, in every parallel thread of reality that the universe has been weaving since the beginning of time, in a structure so vast that the observable universe, with its 200 billion galaxies and its 13.8 billion years and its 10 to the power of 80 atoms, is one branch among a plenitude beyond all description. The terrifying thing about quantum computers is not that they will break encryption, not that they will outcompete classical systems, not that they will make some countries more powerful than others. The terrifying thing is that the most honest reading of the physics underlying them, The reading that takes the Schrödinger equation seriously as a description of reality and follows it without adding any extra rules describes a universe that is not the universe. A universe that is one branch, yours, and the calculation that tells you this was completed in 200 seconds.